Good morning, everyone. I hope most of you are awake, at least not jet lagged. So, as you might have seen just from the previous slide, there is a change in schedule. One speaker is unfortunately not able to make it. That means we will have a little bit more time for each talk, so more room for direct, short questions. So before I get to my talk, I would like you to guys to go to that link in the second bullet, gmp3.cnf.io. This is where most of the live Q&A will happen. I think even through the main conference. So you were able to go there? Yeah. No, I want to. Adil wants to test it, so. Our course is, I think, listed under afternoon session. So just look for the title, taking control of neuroimaging quality data. Should be some questions there, so we'll get there. I think the system will take you to the right question based on the slide, right? So, all right. Yeah, I did, but they're at the very end. Yeah, yeah. All right, let's get going. I think it's enough time. So I'll be starting with a talk giving you a rough overview of neuroimaging quality control, followed by some details into how different use cases of different QC use cases of anatomical MRI. This is the rough schedule. After that, there is going to be a break at about 9:45 a.m. And an open panel discussion at 11:30, where more open-ended and longer questions can be asked. Okay, so in this course, a half-a-day course, will mostly be focusing on these three modalities: anatomical, functional, and diffusion, with the goal to raise awareness of the issues and education in awareness of the issues and to try improve education in neuroimaging quality control. I guess a lot more practical intuition than physics education, so to say, into the QC aspects. I'm gonna, before I begin my talk, will give you a quick terminology definition, so to say. I think these are important to keep in mind, although there may be a bit of a mix in how they are used. For example, quality control, quality assurance, what the different stages in QA, QC are. So a subtle point that's often missed in this discussion is the difference between quality assurance and quality control. So given a pipeline that looks like a multi-step pipeline that looks like this, starting with some neuroimaging input data that ends up with some output, QA is quite often process-oriented. They're trying to focus on improving the quality of the process in the hope that the results will be improved. And QC is most often focused on the final product. That's the major difference. You want to keep that in mind. And sometimes, often, they are both interwoven in the way they are implemented, but it's still good to keep the difference in mind. So the goal, the focus on QA, like I said, is on the whole process, whereas for QC, it's on the final product. Whereas the QA tries to prevent defects, QC tries to verify quality. Right, so that's the big difference. Oh, I forgot to mention, all the slides will be posted online, so you don't have to worry about scribbling all the details, taking pictures, so you can focus on this. Yeah, another important term, in my opinion, is artifact. used in different ways, mostly any error in the perception or representation of the information. I think that's how I think about it, or simply a defect or distortion in the data or anomaly or even unwanted data, so to say, right? So in medical imaging, typically we're thinking about misrepresentation of tissue structures, right? Um, yeah, we will probably define a lot of artifacts in different modalities, like I mentioned, and provide intuition to them. But we may not always present a way to correct for you, um, guys. And sometimes solutions exist, but other times they don't. Often you find issues, you have to discard the data. Um, that means it's an opportunity for you to find a way to correct them, in my opinion. So, to give you a full scope of neuroimaging, for example, this is a typical setup. We have various modalities, like I mentioned. In my opinion, I think QC is not just what is in the image. It goes far beyond that. For example, it starts with maintaining the facility where the scanner is housed and the acquisition happens in terms of climate and hardware. That's followed by scanner QC, calibrating it and performing phantom corrections and maintaining other phantoms performance. Followed by the session QC at the particular day to ensure the scanner is in a known state, followed by the actual neuroimaging data QC. Look for artifacts such as ringing, motion, and other types. And then, usually nowadays, with the emergence of big data, and there is a lot of multi-site and multi-scanner issues as you try to consolidate the data together. So, one of the important things you take away from this course, I hope it is this, that QC is not just what is in the image, that there is a lot more things that go into the fuller framework. And like I mentioned, some of them are more QA and some of them are more QC. They might both be mixed up in some steps. So this gets me to the actual first talk on T1 weighted anatomical MRI. This would be focused on mostly describing the common artifacts you see in them, just giving you some ways to some intuition into which processes cause them and how severe they are, what are the different levels. So the common sources of artifacts in this modality can be roughly categorized into these 4 categories: experimental error, subject motion, some hardware issues, followed by some reconstructions error. And I'll probably describe them in isolation, but they can happen together also. So this is to give you some screenshots of different artifacts, and I've copied many examples from this wonderful manual from NGH. You can also download that online. So the first of the artifacts in this modality is something called wrapping. For example, that's something that looks like this. I think screen is pretty good to see all the colors, right? Even from the back. So there is a little red circle. Even in fact, it's funny that even the circle is wrapped. So you can see the nose that's wrapped around the edge. So the primary cause for these artifact is picking up signal from outside the field of view. And you can easily detect it by visual review of the image, and typically it's either usable or not usable depending on how much and where it's getting wrapped. For example, this I think is not usable for analysis. The other one is. So the second artifact is something called clipping, where for example this is a good T1 image, and a clipping artifact would look something like this, fairly easy. And typical causes are operator mistake, bad field of view, or subject motion once the session is set up. And again, you can easily detect it by visual review of the data. And what you want to look for is brain appearing unnaturally flat. So if like this is clear, right? Um, and usable depending on how much and where the clipping is, right? So in this case, I think we might be able to use it for some subcortical analyses. Like I said, all these issues will be described individually in isolation, but they can occur together, right? So another common artifact in this modality is something called ringing, striping, blurring. It's called many names, and the reason for these types of artifacts are diverse, including subject motion, hardware, and some software issues too. So the way they appear, you can't really distinguish them, even though the source is slightly different. So the people tend to put them in the same category. And the easiest way to detect them is to perform visual review. For example, in this cross section, I hope you can see that. You can see the ringings. For example, I highlighted there. So as I flip between it, you can probably see it, right? So you want to look for unnatural anatomy in the brain that is not naturally occurring, and ripples are bands that mirror the curve of the brain, right? So, that's the curve of the brain that typically follow, and different levels of severity. So the next artifact is something called shadowed arc, and its primary cause for it being undersampled data, typically in parallel imaging acquisition scenarios. And very similar to ringing, you see curved stripes. For this artifact, they're mostly through white matter. For example, in this case, you can see that here, right? So I flip between them for a bit. These are easily detected in the axial view, and for example, give you more severe form of it. That's the kind of curved stripes to the white matter you're looking for this artifact, and this can be in different levels of severity. This is another extreme form of shadowed arc artifact. I think this is also referred to by residual motion. There's a few different names. Yeah. Next artifact is something called ghosting. You can see why it's called ghosting. Variety of causes, and the most common being subject motion, and for this artifact. And what you want to look for is a displaced copy of the brain, like a fainter one that's stamped again into the image. So, for example, this is a good slice, something that looks like this, as if another. So, and sometimes even upside down. This can easily be detected in the viewer by reducing the maximum intensity. So the next type of artifact is something called RF noise. The primary cause for this is signal interference that is typically additive. So a loose connection or conductive debris is another cause, which does have a clear effect on the signal. It's not just noise. And even simple clothing such as a belt can cause this RF noise. And you want to look for uniform light. For example, this is mild level of this artifact with regular viewing, as in normal maximum brightness. And if you reduce the maximum brightness, it becomes really apparent in this case. So it's usually straight, rigid, and organic. Does not follow the curve of the brain, unlike the other ones I've described just a few minutes ago. Different levels of severity for this too. I'll give you more examples now. For example, this is pretty bad. Is another really bad artifact. this is the streaks that you might see, right? So usually, like when you see something like this, it might look it's localized, but I would think it's just the tip of the iceberg. So you want to look for other signs of issues in the data too. So this is another example of lots of noise. So the next example is next artifact is called the susceptibility artifact. The primary cause for this artifact is metal, presence of metal in or near the scanner. For example, dental work or a metal hair clip, and even colored hair dyes cause this artifact. And like if something as mild and subtle as colored hair dyes happen, it can be really hard to detect unless you pay a lot of attention and specifically look for it. So for example, that's the susceptibility artifact in this particular cross section, most likely due to clips, dental clips. And you want to look for a natural black area or a type of a hole in that location. So for example, this is another susceptibility artifact. So this is the black hole I was referring to, and it's usually bordered by a bright band such as this due to the sudden changes in magnetic fields in presence of the metal. If it is fully outside the ROI, I think data might be sometimes usable, but it really depends on how it's acquired, but you want to keep that in mind. So, like in this case, so this is bad, very bad, I don't think it's very usable. This might be, depending on how the full volume is. So the next artifact is something called abnormal inhomogeneity. The cause for this artifact is common cause is one of the coils malfunctioning in the setup. Just it's important to note, I think most systems, most multi-channel RF coils do have some inhomogeneity in them. Maybe sometimes they're designed for it, but what we're looking for is something that's abnormal that for that particular coil, right? So give you more intuition. For example, if you increase the minimum brightness, it becomes even more apparent, the abnormality in the inhomogeneity. So it can be easily detected by checking for symmetry in contrast, right? So left versus right, as well as front versus back. That's the easy way to detect it. And if the contrast is not symmetric between front and back and left and right, then that's an artifact. So to give you more intuition into this, in these two slices, to the left you have what appears to be normal contrast, and the right is what is high contrast, and I don't see much inhomogeneity in contrast, either front and back or left and right. So for example, if you look at this particular two slices for different levels of contrast, it's inhomogeneous and actually abnormal for this particular coil. That's pretty obvious on the right? So, like I mentioned before, this is about learning to detect them, giving you more practical intuition into it, not less physics behind it, right? So, there is a collection of paper we maintain in the Jotaro collection by Neuroimaging Quality Control Special Interest Group. You can always go into those papers to get more physical understanding of these issues. So those are the common artifacts. Now I'm going to give you a few practical use cases for people who are interested in actually analyzing T1 weighted MRI data. That includes whole brain reconstruction from FreeSurfer, which is quite popular, cortical parcellations and subcortical structures, and volumetric segmentation, followed by how we can perform alignment checks, both in the case of unimodal T1 to T1, or even cross-modal PET, EPI to T1 or PET to T1, for example. Right. So FreeSurfer is a complicated processing pipeline involving a large series of complicated steps, which means that a lot of room for errors, and they're typically categorized into these. So errors in skull stripping, segmentation, intensity normalization, misplacement of the PL surface, topological defects, and this is even for a successful run on an MRI scan without any like major issues like disease or other things. So because it's a difficult task, these errors tend to happen. So easiest way to assure its quality is to perform visual review on QC. So to give you more intuition, these are the typical outputs from free surfer. This is the white matter surface, the gray matter surface. This is how they appear in a particular cross section overlaid on the T1 weighted MRI. And most often our people are interested in the accuracy of the cortical thickness estimates that are provided from this parcellation, because this is a great biomarker candidate for a lot of different diseases. Ensuring the accuracy of these two surfaces is critical. And if you a parcellation visualized on the surface would typically look something like this. This is the volumetric segmentations as you seen before, right? So a few examples of skull stripping errors. On the left, you see that too much brain is removed, cerebellum. On the right, too little is removed. So this is just to give you some intuition into this. And segmentation error often look like this. For example, in the sagittal view for hippocampus overlaid in cyan. It's not. You think you can see it? It's overestimated. It's actually very badly wrong, even on the right too. And this is more examples for subcortical volumes. In this case, for example, I think these two areas are erroneous, right? And even for lateral ventricles, which are actually often quite easy to segment, there are issues with free surfer due to many reasons. So you need to visually review them for accuracy before any important analyses. And more importantly, this visual review needs to happen in this multiple view if you want to care about voxel level accuracy. So I would say triple check is necessary sometimes, because what can appear as error in one view might not be in this case, as you can see. This is an example of good parcellation. This is an example of very bad parcellation, right? Just to give you two extremes. And they can appear as something like this. For example, you can see that green overlay is too jaggedy, noisy, so that's very bad. And another bad example is a big hole from central sulcus all the way to the frontal area, red lines. And often this used to be performed in a traditional sense using a typical viewer, which can be quite time consuming and erroneous. And nowadays more integrated approaches exist that make the whole process easy and accurate. And one more important use case for QC in T1 weighted MRI is to knowing how to do alignment checks quickly. So common requirement is, especially if you have if you need to ensure alignment to an atlas, for example. There are many ways to do this. One of them being just flipping back and forth between what you need to check alignment between, followed by you can actually mix the two images as two color channels in the RGB spectrum, which makes it really easy to detect them. For in this case, the red is one image and green is the other one, and you can see that they're clearly out of alignment. And another way to do it is something called checkerboard pattern. You display different images in the neighboring cells, left and right, or top and bottom. And when they are similar or more or less aligned, you don't see much jaggedy edges. For example, when they're dissimilar, it will become really obvious. And another way to do it is to extract edges and overlay them on the image, which makes it quite easy. So it's important that you check it in many slices, because what seems aligned in one view or one slice might not be. So for example, you want to look at the three views, multiple cross sections, even with edges, for example. Or if you take a simple difference image, actually, it can inform you a lot about a lack of alignment in particular two particular images. So when you have to do it for cross-modal alignment check, it gets a little tricky. This simple color mix or checkerboard, it's not often very useful because of the differences in contrasts as well as resolutions. And edge computation is also pretty tricky. So animation-based checks, in my experience, have proven extremely valuable. Just simply flipping between the two modalities, or any number of modalities, so to say. In the case of quantitative MRI, can really help check alignment quickly. So that concludes the first talk. Are you guys ready for some questions? So remember that web address that I showed you, gmp3, I believe, .cnf.io. Is this working on the, yeah, okay. We'll give you 15 more seconds to answer this. gmp3.cnf.io, I believe. Oh yeah? Excellent. No. Oh. Okay. So let me see.
This 100% of the audience got the correct answer of motion that voted.
Perfect. See, I did a very good job. Okay, the next question is this. What's the common cause of susceptibility artifact? Another 10 seconds, maybe 5 seconds. Yeah.
Everybody got this one too.
Perfect. Excellent. The next one. Which one of these is not necessary to judge the accuracy of cortical parcellation? Tricky question, I guess. All right, is that 100% too? I guess I didn't cover this as well as I should have. But the correct answer is cerebellar segmentation. It's actually a little tricky. Usually this is not necessary. Maybe I should say that. So